Welcome and hello. This is a video exercise using the HEC RAS controller. We're going to do a Monte Carlo simulation in this exercise. Monte Carlo simulation is a statistical method used to model and analyze systems that involve uncertainty or randomness. It works by running many repeated random trials to explore the range of possible outcomes. The results are then analyzed to estimate probabilities, averages, variances, confidence intervals, and risk levels. So let's go ahead and get started. We got HEC-RAS up on the screen here. I'm going to start from the very beginning, describe the process, build the model, and then use the HEC-RAS controller to automate this Monte Carlo simulation. All right, so let's get started. I'm going to go File and New Project. So we're going to start from the very beginning here and just build things from scratch. Go ahead and navigate to where you want to save your project files. So for me, it is in this HEC-RAS directory. I'll just call it project. And click OK. And we'll be using English units or US customary units. Edit geometric data editor. I'm going to sketch a river reach, just boom, something simple like that. And then I'll call it river A and reach 1. It's going to be my only river and my only reach. So these will both be river ID 1, reach ID 1. As far as the randomness goes in the Monte Carlo simulation, I'm going to have some random inflow data, and we're going to run the simulation over and over and obtain the water surface elevation at a specific cross section. All right, so that's where we're going. Let's add some cross sections to our reach now. So options, add a new cross section. Let's start by putting this at the bottom of the reach, river station 0. I'm going to paste in some station elevation data, just something generic like that works. The distance to the downstream is 0. Manning's N, I'll use 0.035 and 0.05. The left overbank will be 40, the right overbank will be 100. Cross-section station, I. All right, I'm going to add one more cross-section manually here at the top, and then we'll interpolate a few between. So I'm going to go options and copy the current cross-section. The upstream cross-section I'm going to put at river station 1000. Click OK. I'm going to use all the same numbers except increase the elevation by 1 foot. So options, adjust elevation, 1 foot. So that would be a 0.1% slope downstream. And I also need to add the downstream distance right there. Okay, apply, and there we go. Next, we'll go Tools, Cross-Section Interpolation within a reach. And then for this reach right here, the only reach we have, we will add a cross-section every 100 feet, interpolate, and close. Cool. And then the last thing I want to do here is be able to zoom in and pan a little bit easier. So let me just modify the extents here. This is not geo-referenced. I do not have the terrain. This is a simple 1D model. You guys saw me start it and build it. So yeah, okay, cool. So now I can add a inline structure is what I'm going to do. Right down here at River Station 280. So I'm going to go inline structure, options, add an inline structure. And put it at 280. That's going to be the upstream edge, and it's going to be 30 feet wide. So I'll click OK to that, and then we're an embankment. The distance will be 20 feet to the next upstream cross section. The width will be 30 feet, and then the station elevation data, I'll go 0. We'll have a top elevation of 318. You'll see that in just a moment, 140 and 318, and then 0 on the side slope. Okay, so I'll click OK, and then boom, here's our inline structure. That's going to be, at River Station 280. Next, I'm going to add a culvert. So boom, there's the culvert. I'm only going to have one culvert barrel, so it'll be in its own group. It will be circular. It will have an 8-foot diameter. It'll be concrete. The distance to the next upstream cross section is 20, just like the inline structure itself. Culvert length will be 30, just like the width of the road. And then let's see, let's go 0.5 for entrance loss coefficient. Manning's N, we'll go with what's typical for concrete, 0.013. And then let's see, the invert, I'm going to use 301 for both upstream and downstream. We'll see that in display in the cross-section view in just a moment. I'm only going to have one barrel, so I'll give it a name of B1, the upstream station and downstream station. This is the cross-section station now, so we're going to put that right in the middle, which is at 70. Okay, so if I click OK to that, we now have a single barrel culvert right down here, which is how the water is going to pass through this particular inline structure unless there's too much water, in which case it's going to overtop. So this elevation here of 318 is going to be critical for us a little bit later in the exercise once we're running the simulations. 318 is the elevation of the top of the inline structure. So that's why I mentioned that. Okay, let's close that. Now in the plan view, we can see our inline structure. So that looks good. Best practices would probably be to put another cross section just downstream of the inline structure, a little bit closer than, what, 50 feet away, but it's all good. Let's go ahead and save the geometry. So File, Save Geometry Data. We'll just call this base and then OK. All right, done with that. Let's go ahead and add some flow data. This is going to be a 3-day simulation, and we're going to have an unsteady flow hydrograph. We're going to be routing through this river reach multiple times, but first we need to set it up manually. After that, we can manipulate the flows with each iteration using the VBA code. All right, so I'm going to go up to Edit and then Unsteady Flow Data. For the boundary condition, let's first set the downstream boundary condition to normal depth, and we use 0.01 for the slope of the channel. So we'll just use the same thing there. It's a close enough approximation for energy grade line slope. And then the upstream boundary condition, I'm going to use flow hydrograph. And then what I'm going to do is set enter table and then also use simulation time. That way I don't have to remember exactly which time the simulation starts. It's synced up automatically. I'm going to use a 1-hour time step, so that's good. Next, I'm going to open up an Excel file that I've prepared specifically for this lesson. And boom, here it is. So what you're looking at here is time series data. This column number 6 is what I'm talking about first. This is hourly inflow data to the upstream end of the reach. This is what we're going to assign our flows to for that boundary condition that we're dealing with here. Over here is the mean flow, and this goes down for 72 hours. See, 72. The base flow is 180. That's what it starts at, and that's also what it ends at. But then you can see I've plotted that average inflow in blue, and then the synthesized inflow is in orange. So it's just going to automatically recalculate every time the worksheet recalculates. So the blue values should stay the same, even though the vertical scale may be changing on occasion. So you can see the orange dots right there. That's the actual synthesized inflow that I'm going to be feeding into the unsteady inflow file one trial at a time. But just to get our first one done and to run the model manually, just using the user interface, the boring way, then we're going to have to just input the data manually. So that's what we're doing first. I've got some existing results that I need to clear out so we can do this again. Over here is where we're going to be generating our results. All right, so I'm going to just put these values right here onto my clipboard by Control C and selecting them. Well, select them first, then Control C. Come over here to HEC RAS and then Control V to paste. I believe that pastes them in. Yep, that looks good. And if I click on the plot data button here at the bottom, boom, it gives me an image of that inflow hydrograph serving as the upstream boundary condition for my river reach. If I want the actual numbers, boom, here they are. All right, so that's looking good. I can close this up. I'll click on OK. Now I need to save this unsteady flow file. So File, unsteady flow data. We'll call it base and OK. All right. Let's go ahead and run the plan now and go run unsteady flow analysis. We have the geometry file, the unsteady flow file. So we'll just call this base as well. And then the short ID, I'll just call this base sort of as a base case. I'm going to toggle on the geometry preprocessor and the post processor, and of course the simulation. I'm going to run this for the first about 3 days of the month October 2015. So it'll be from the beginning of the day to the beginning of the 4th day of the month. So through October 3rd is what's happening here. And then all the other settings I'm going to leave as is. So the computation interval, all the computation settings look good. So File, and then Save Plan, and then Compute. So we're running it manually. We'll take a look at the water surface elevation at that inline structure. Okay, that looks good. I'll close that, close, and then let's first take a look at the cross-section data. All right, so this particular profile right here is the maximum water surface elevation. But if we animate the computations or the simulation that just was performed, then this is what we're looking at here. I could press the play button and then it would kind of see the water surface elevation right there, the blue line. It looks like the culvert is fully flowing for the entire simulation, so that's good. And we can look at other cross sections as well. Of course, the cross section of interest for me is right here at the inline structure. So we may be asking questions like, how high does this inline structure need to be built up? Or perhaps how large does this culvert barrel need to be in terms of a diameter or the number of barrels? So there's lots of different possibilities for different analyses. I'm going to close that and then I'm going to take a look at the maximum water surface elevation. So I'm going to go profile. This is the profile summary table or profile output table as it's called here. And then I'm going to take a look at the inline structure and then take a look at the maximum water surface elevation. So this is the very last profile of the simulation. I want to change the profile to maximum water surface and then remove that other one. Click OK. 319.19 is the number. So on my results Excel file, which I have right here, let me go back up to the top. That would be my first trial. So I'd say trial number one, 319.18 feet. So I could perform this calculation multiple times with trial two, trial three, trial four, and so on. Then I would have other numbers here like 318, 320, 317, whatever, based on the random inflow that we're using as an upstream boundary condition to that reach. And yeah, so let's go ahead and get that going. So over here to the left, I know I didn't talk about generating the inflows too much, and that's a little bit beyond the scope of this exercise, but there's more could be said about that by how to synthesize some of these inflow hydrographs based on historical data and also performing some sorts of statistical best fit distribution analysis. So that was all sort of taken care of beforehand. But anyway, what we're going to be doing is running this simulation 200 times for an 8-foot diameter single barrel culvert and then later a 9-foot diameter single barrel culvert. And we're going to see what sort of results we get. So that's the direction we're going with the remainder of this exercise. I'm going to save my Excel. And what we're going to do is click on Developer tab. If you don't have the Developer tab, click on the File menu, come down to Options, and then you're going to want to go to Customize Ribbon, and then make sure you have Developer right here checked on, and then click OK. Click on Developer, then click on Visual Basic. All right, now let's move this right here. This is where I'm going to type in the code to operate the Monte Carlo simulation in the HEC RAS controller. I'm going to double click on worksheet one. This is the file that we're editing. So this is my interactive development environment. And I'm going to start by pasting in my main subroutine. So this is going to be the primary subroutine that I call, and it will call other subroutines as well. So what we're going to be doing is looping. The number of trials is going to be 200. We are going to initialize a row results and column results variables, just so we know where on the worksheet to begin writing the results out to. We're going to increment the row for each new trial from 1 to 200. And we're going to print that trial number on the worksheet in column 8. So that's going to be in this column right here. Plus, I'm going to have a running number right here in see row 2, column 8. Back here. Next, we're going to create a new inflow value, and we're going to save it to the .u number file. That's the unsteady flow file that's associated with our plan. And then after that, the final subroutine is to actually compute RAS and record the results. So this much is pretty straightforward. What we still need to explain is this right here. Let's first talk about how to create a new inflow file. So if I scroll down here, get myself some room, just paste it in this subroutine right here, loads a new inflow data. All right, let me go ahead and see which file it is exactly. All right, so right here in the file GUI under unsteady flow, the title is base. Then the file itself is in my project HECRAS project.u01. So I'm going to open that up. Here's my project directory right here. I should see a project.u01. Okay, let me open that up just in a text editor. Okay, I've got that open and it's on the screen right here. So here is the unsteady flow file. And the line I really want to focus on is line 7 right here. This line 7 has the 73 different flow rates that we're going to be using in our simulation, one flow per hour. So this is the 175.9, 181.1, 193.1. What you may or may not notice is that every 10 numbers, there's a line break. So right here, you can tell there's a line break because there's 8 on the first line. Really, there's 10 on the line, but it breaks right here, and then right here, and then right here. So what we want to do is write a script that will update these 73 records. And I should probably also point out that each of these values is delimited by 8 characters. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. So we need to be wary of that. It's not comma separated values, but it's 8 characters at a time with a line break every 10 numbers or 10 entries. So that's how that works. Everything else in this file can remain the same. We're just using the same river reach. We're going to use the same time interval of 1 hour, 73 records, and everything else below here is also just going to stay constant. Okay, so I'm going to close that up. Actually, you know what? Let's go ahead and just leave that open for now. And then here is the file. We're opening this file right here, project.u01. That's our unsteady flow file we were just looking at. We're going to read in the text to that file. This file lines is an array of string. Each line from that file is in a entry within this array. We're going to update only, let's see, line 7, which would be index 6 in this file lines array. So ultimately, that's what we're doing right here. File lines index 6 is going to be updated with this flows formatted string. The flows formatted string is going to get the flow formatted string for each flow rate that's read in from the worksheet and then converted to a string with 8 characters that have spaces to make sure that it's 8 characters long. So for instance, if the flow rate was 250, then it would be 5 spaces 250. That would be the flow formatted string, and that will be concatenated with all the other flow formatted strings. Okay. So what we're doing here is basically just looping through this column number 6, starting at row 6, and then going all the way down to row 78 to get the 73 different records that are going to be populating that string. And then ultimately, we're going to be putting into that line 7, which is in file lines 6. This right here is just writing back to the file and close. So we can run this subroutine independently and then just confirm that we're getting new numbers, not only in the Excel file, but also in the text file itself, this project.u01 file. So what I want to do is pull up this file again. Let me move this out of the way. We can just do a quick demo here. So load new inflows, and then let's go ahead and run that and then click over here. Okay, cool. So it's telling me a new version is available. Do I want to reload? The answer is yes. And then boom, all of these numbers have now been updated. So 201.5, 186.9, 141.5. Those are the first 3 out of 73 flows, which should have been generated right here. 201.5, 186.9, 141.5. So now that we've got that part of the process automated, now we can focus on the HEC RAS controller, running the simulation, and printing out all the results in this table over here. Okay, so let's go back. We can close that. Here is the VBA. I'm going to scroll down here, and then this is sort of a utility subroutine just for me to be able to open up HEC RAS a little bit quicker. Don't mind that. All right, so what I just pasted in was an open project subroutine as well as compute record. So compute record, this is what's called from the main subroutine right here, compute record. We're passing it the row and the column where we want to print the results. We're first going to start by creating a HEC RAS controller. We're going to open up the project, which is project.prj. So that's that. For that, we will compute the current plan right here, which is using this compute underscore current plan routine. We're also going to hide the computation window so it doesn't show up on the screen over and over as it opens and closes. No need for that. Next, we're going to actually get the maximum water surface elevation by using the controller's output node output function. That requires a river ID, which is 1, a reach ID, a node ID, UPDN, profile ID, and variable ID. The variable ID is 2. That's the water surface elevation. The profile ID 1 for an unsteady flow refers to the maximum water surface elevation, so that's nice and convenient for us. UPDN refers to the upstream face of a structure, if it is a structure. And then node ID 9, this refers to the ninth node from the upstream end of the reach, which happens to be our inline structure. And then river ID and reach ID are both 1. There's only one river and one reach. Maximum water surface elevation value is then rounded to 2 decimal places and then printed to the screen, to the worksheet, the specified row and column. Right? Then we save and close .ras, and then the whole loop repeats after that. So without further ado, let's just go ahead and run the main routine and see if this works. So column 9, 200 trials. That looks good. I'm going to pull this off to the side here so we can see the results build right here. And I am running it. So let's go ahead and see what happens here. First, it's going to be running the first trial. So that's what's happening right now. Okay, so the first trial is completed. It's working on the second trial. The first trial came in at 319.42 as far as its maximum water surface elevation. The second trial should be showing up any moment now. From testing, I realized that this is taking about 5 or 10 seconds per iteration. Okay, there we go. 319.57. All right, the third trial is 318.81. Okay, embarrassing mistake, but you probably saw me do it. Back when I was editing the cross section, I had 35 right here instead of 0.035. So I went back, I found the error, I fixed it, I changed it for all my cross sections. We're going to go ahead and save that now. So File, Save Geometry, and then we're going to run the simulation once again. So our maximum water surface elevations here are probably going to be a little bit lower than they were when we ran it the first time. So hang tight here to go back to main and then save it and then run the main subroutine. All right, so let's take a look at some of our numbers. Before we were getting numbers closer to like 318, 319, 320. I would expect it to be a little bit lower here. 318.48. Okay, still pretty high. 313. Okay, so that makes more sense now. Okay, so I got that all finished up. We have 200 records right here. So you can see the water surface elevations right here from 1 to 200. And it looks like we are close to that 318 top of the lateral structure. In fact, I'm going to perform an, let's see, count. It's called count if, and then the first argument is the range of values, and then comma, parentheses, greater than 318. So I'm just curious how many records we had greater than 318. 20. So that out of 200 is 10%. If that's not acceptable for whatever reason, we can increase the size of the culvert barrel. So we're going to do that, run the simulation again, and then check to see what's the approximate percentage of random inflows based on our distribution exceed that 318 foot water surface elevation threshold. All right, let's go back to open up HEC RAS and modify our culvert barrel geometry. So 1 second while I open up my project again. I got my project up on screen. Boom, here's the inline structure. Let's open that up. Let's click on culvert. The only change I'm going to make here is change the 8 foot to a 9 foot for the diameter. Everything else looks good. I'll click on OK. So we can close that, file, save the geometry, save the project, close that up. The other change that I'm going to make right here, it's minor but still important, is to change this results column from 9 to 10. We don't want it overriding the existing results from our 8-foot barrel diameter. So this is now a 10. We're going to be running it 200 times. That's going to start when I hit save and run the subroutine. All right, number 1, so it should populate right here. We would expect lower water surface elevations in general. So it looks like the previous average was, I don't know, 315 or 316, just glancing at the numbers. So 313 to start, but again, that's just one number. That could have been with an inflow that was less than average. So, okay, I let that run. boom, here are our numbers. Just glancing at it, it looks like the water surface elevation is lower. Let's just copy that previous calculation over, and it looks like only 2 out of 200 trials exceeded a maximum water surface elevation of 318 feet after upsizing the culvert from 8-foot diameter to 9-foot diameter based on our inflow distribution, our inflow hydrograph, which was randomly generated, which is the spirit of the Monte Carlo simulation. So clearly, there's a lot of other analysis that we could perform. Perhaps we wanted to check the threshold of 320 feet or 315 feet in the event we wanted at least 3 feet of freeboard, whatever. We could change the culvert sizes, the number of barrels, on and on and on. But I hope this gave you an idea about how to utilize the HEC RAS controller by updating the unsteady flow file and using a Monte Carlo simulation to analyze a system like this.